It had already allowed it, but it was asking me again, so it froze. I don't know.
I see.
I don't.
Okay, I'm just setting up the slides. Okay, there we go. Yeah, so we do have a newcomer. Sensei, is that the way to pronounce it? Oh,
Yeah,
he's saying no camera, but that's fine. Do you have audio?
Yeah, can you hear me now?
Cool. Yeah, we can hear you.
Yeah, my name is Paul. I don't have a camera. I've somehow managed to teach university classes without it so far. So usually I have a presentation or do some live chalkboard stuff. But
did you say your name is Todd?
Paul.
Paul.
Can you hear Paul? Okay.
No, yeah, I'm Zartaj.
Nice to meet you all.
Yeah.
But yeah, so I've been off and on over many decades looking at this stuff, and I have the, I guess, second edition of some books, first edition, third edition, different editions of books from here, and I think I have the facile somewhere, but I can't find it at the moment. I have way too many books. And anyway, I thought it was interesting. I saw it on Meetup. I thought interesting to find out what's going on, and can always use some motivation to dive back into this stuff. Things get busy, and so it seems like an interesting group to see how things are going here.
Well, it's great to have you on board. So really happy to see you join in. Where are you connecting from geographically?
I'm in Northern Virginia and Reston area.
Ah, okay.
Yeah, and I've also done a lot of tech and PS tricks in the past for various things, and so I've followed the literate programming and C-Web for quite a while, and just kind of curious what the next step in that evolution is as well. I don't know if anybody's interested in that areas, but
yeah, so our focus is really the art of computer programming books. There's a lot of material there to cover. And, I don't know if you had a chance to look at the YouTube videos so you can get a sense of how we're progressing and what our process is. But as I was explaining to James just a few minutes ago, we are kind of jumping through the books, and the idea being that just to get as much of a foundation to allow us to look at more modern stuff, more advanced stuff, but we do intend to cover the fundamentals. So it's not like we'll just skip stuff for the sake of skipping. However, I will say that we do focus on the algorithms and the code and the programs, and not so much the analysis. If the analysis does come up or is really significant in some way, we'll talk about it or we'll discuss it. But I feel like spending time on analysis would be, it would take so long that would be kind of like a whole separate set of meetups. And then you'd also need to cover a lot more of the mathematical preliminaries. So we've managed to avoid that a little bit, but Yeah, at some point, we will probably need to cover a bit more of the math, but that's how we're going. Um, so today, this is the agenda for today. We are starting the third. Oh, I made a mistake here. This should be volume 3, actually. And the chapter on sorting is the one that we will be doing. And this is just a few of the initial pages from section 5.2. So 5.1 is not strictly sorting, it's more like a mathematical foundation for sorting. And in the books, it is marked starred as well, so it's considered optional even by Knut. So we're skipping that, just going to 5.2. And there's a couple of algorithms there that we'll cover. And then at 3, generally around 3, we take a 10-minute break. And then if there's material left over from the first half, we'll continue with that and finish that. If we have time, then we do some exercises. And after the main session is over, then what I've been doing for the last couple of meetups is to step through one of the programs, the MMIX assembly language programs in the visual debugger. And again, I'm really happy for anyone to stay and keep me company and, keep the video and the presentation enjoyable that way. But, if you have to go, that's fine too. I'll just continue with the demo, and then it'll be available in the video later. So here's the process. So most of us are familiar with this. And by the way, for Paul, right? Is it Paul?
Yes.
Paul. For Paul's benefit, here's just a synopsis of our process. Generally, we will read a couple of pages at a time, just enough for about 5 to 7 minutes worth of reading. And then we'll discuss what we've read, if there's any questions, if there's anything to work out, if there's any comments, whatever comes to your mind, we'll talk about it. And then we just continue with that. So, and I'll have a slide saying what we're reading and whether we're discussing or not, and so on. And feel free to keep typing into the chat whatever you want to discuss or whatever your thoughts are. And I'll post the chat copy to GitHub afterwards. So we start with, again, I'm sorry for the typo. This should be volume 3 and chapter 5. It's page 73. We'll spend about 7 minutes on this. Reading till about 2:22. Okay, so how did everyone answer for that first initial question about how would you construct a solution to that problem?
Let's see, I probably would have done it as a exchange sort.
So you did an exchange sort. Can you explain how you actually sorted those items?
Well, basically, let's see, for 5, let's have, I'm thinking for 5, I probably would have gone for a small loop. If it was like, 3 or 4, I may have just unrolled it and did a whole bunch of ifs. But basically just have a loop going for 1 and 2. Compare them, swap them if necessary. 2 and 3, 3 and 4, 4 and 5. That should make sure that 5 is, the largest one is in 5, and we're not too sure about the other ones. Then you just have to go again up to 4, swapping which ones are out of place, and then up to 3, and then just 1 and 2, see if they're out of place. And in the end, they should all be in the right place.
Okay, how about everyone else? What technique do you think you used from among these? I guess there's 6 of them, including the new super sorting technique that nobody knows about.
Yeah, well, there's really 2 different ways of exchange sort. One's what you just described as a rock sort, and they have a bubble sort, which is the same kind of thing, except you exchange with 1. You compare 1 and 2, and if one is, whichever one is the smallest, you put in position 1, and then you go to 1 and 3, and whichever one is the smallest, you put in the. So at the end of the first loop, the first element in the list is the smallest, or is the smallest, or the first in the sort, and then you start the loop again from 2 to 5, and then from 3 to 5, and then from 4 to 5, and you're done.
Mm-hmm. Okay.
So that's and I guess a rock sort would actually be comparing 1 and 5 and putting the biggest one down at the bottom. So what you described is actually different than both of those. Mm-hmm. You'd start comparing 1 and 5, the biggest one would go to position 5. Then you go 2 and 5, 3 and 5, 4 and 5. And then you'd start again from 1 to 4, and then from 1 to 3. That's a rock sort. So the one you described is a little bit different, I guess. I don't know. Mm-hmm. It ends up like a rock sort. In other words,
yeah.
Every iteration of the loop is guaranteed to put the biggest one at the end of the loop, and then you do it from 1 to 5, from 1 to 4, from 1 to 3, and from 1 to 2.
Mm-hmm. Right. So it basically is like, doing the same amount of work. It's moving things further, which probably doesn't make much difference.
It might. It might.
Yeah.
All right.
If you were sorting on a tape, it definitely would. If you were sorting on a disk, then if distance apart was, yeah, it could. Actually, even in memory, when you get to, like, you have L2 cache and pages, it could make a difference.
Mm-hmm.
Miguel or Paul?
So I took undergraduate computer algorithms in the 70s, and they used the term rock sort and bubble sort then. Do they do that now?
I haven't been an undergraduate in a very long time, so I wouldn't be sure. And I haven't looked at any recent textbooks either, but I would say that they probably start with like insertion sort and then bubble sort probably, and then go to quick sort. That would be my guess. Yeah. So Paul says bubble sort is the most popular and exchange. So Paul says that he came up with an exchange. So that's sort of like 3 votes for exchange sort so far. How about you, Miguel? Did your approach neatly fall into one of these techniques?
Yeah, I was thinking in. My first thought was, just try to copy the each element to a new table, but and if you find a new one, when you go to the new table, just rearrange them, and then I realized that I can just do that in the same table. So it's just exchange. Yeah, so I end up with exchange.
Oh,
myself.
okay. So that's 4 in favor of exchange. I think I would have done like if it's 5 items, I would have scanned to find the largest one or the smallest one, like start from one end. So maybe the smallest one, and then the next smallest one, and then the third smallest one. So my approach would have been a selection sort, like just sort of intuitively, if I had 5 things to sort without forgetting everything that I know about sorting or have learned. So
like the rock sort Michael was describing, which I never heard that term before, but
I had not heard that either. So I was hoping Michael would explain that a bit more, but he seemed like we would be familiar with it.
Yeah.
Yeah, it's just the opposite of a bubble sort.
Okay.
So the bubble sort at the end of the first loop, you have the first one at the top. But the way that I look at a bubble sort is you're comparing 1 and 2 and putting the smallest one into position 1, and then you're comparing 1 and 3, and then 1 and 4, and then 1 and 5. I guess you could also do it by starting at 4 and 5 and swapping if they're out of order, and then go to 3 and 4 and swap them if they're out of order. It's the reverse of whoever spoke first. Who spoke first? I'm sorry, I'm bad.
James.
James, you said start from 1 and 2 and swap them if they're out of order, and keep going down until you get to 4 and 5, which will work. It's not the way that I think of as a bubble sort or a rock sort, but it works. Maybe I'm thinking of rock sort and bubble sort wrong. I don't know.
Okay. Any questions about the terminology? Like he's introduced some ways he'll be using consistently throughout the sorting section. Any comments or questions about that? Okay, so let's move on. We are now looking at the first algorithm, which is algorithm C. There's some introduction just before that on page 75. And we'll spend another 7 minutes on this and discuss the algorithm at around 2:37. Okay, does anyone need more time? All right, so can someone summarize the algorithm and the approach?
I can try.
Great.
So the idea is that in a list of n numbers or n things that are not equal, each of them is going to have exactly I minus, I elements that are less than it. If you have so you have like the numbers you put in the chat, 5 minus 2 minus 3. So 6 will have three elements that are less than it. 5 will have 2, minus 3 is going to have 0.
Miguel, would you mind just typing in what's happening to count? Like if we follow the algorithm, how is count changing?
So count is a list of the same size, same number of elements.
Okay.
It starts with everything 0, right? Then we are going to go one by one. So from 5 up to 5. So five is initialized to 0. So the first element.
Just to point out that in step C2, he's actually going backwards.
Going backwards, you're right. That makes more sense.
Okay.
So you do from the nth element. You say from 6.
Okay.
Let's count what we have before. Interesting. So yeah, and then and then it comes from 3. So we're going to count how many elements are less than 6. In this case, it's going to be 3. We proceed to count how many elements are less than 3, which is going to be none.
Why less than 3?
Minus 3, sorry.
Okay.
Yeah, she's just going, and so minus 2 is going to it's going to also be 0 for now. And then 5 is going to also be 0. So then we go to now it starts from minus 3.
No. Just a second.
I misunderstood.
I think you just made one pass for 6,
one pass.
Right? This is like the first pass for 6.
Exactly. Yes.
But for 6, you figured out that there are 3 elements less than 6. So you set the count of the count at index 3. If we're starting from 0, but he starts from 1, so count at index 4 is 3. Right. You've got it. So then what happens after that?
So if I got it correctly, now we begin counting. So I'm not sure now what's next, but I think we should count now from minus 3. Is what would make sense to me.
Right. So we move back 1 in sort of the loop over I. That's now gone to n minus 1. And you're looking at minus 3. Okay.
Right. So we will do the same count for minus 3. In this particular case, the count will stay the same.
Okay, for minus 3, it'll stay 0 because there's nothing smaller than minus 3, among minus 2 and 5. So the count of the index of minus 3 becomes 0 or stays 0, and that's what James has just typed into the chat. And then what happens?
So I'm not entirely sure. Go ahead.
With every comparison, one cell gets incremented. It's either I or J. So since 3 is less than -3 is less than -2, we increment the cell for -2.
Oh, you're right. We incremented it. Yeah, you're right. And he increments it at the same time, simultaneously.
Right. Yeah, with -3 and you're right. Yeah.
Yeah.
And then we do.
Yeah, because otherwise it doesn't work. I was saying, like, wait a minute. When do we find out that that 2 has a thing?
Yeah,
You're
with
right.
6 it didn't happen because 6 was bigger than all of them. But with -3, you have to be careful.
Yeah.
Some count is going to change. Yeah. Okay. Cool. And then, so this is at the end of the pass for -3.
Right.
And then
Then
what
when we do the
happens?
-2, when it compares to 5, it updates both. Updates 5, and then we get a 2,1,0,3.
Could you type that in? Okay, so James typed that in.
Oh, I was doing it. Okay.
All right, and then.
So we're done.
And then that's the order. It starts at the third element is 0. So it's the first is 1. The second element is the second. The first element becomes the second, and the fifth element becomes the third.
Okay.
The last.
Yeah, and then the paragraph after the algorithm, he says this algorithm involves no movement of records. It's similar to an address table sort since the count table specifies the final arrangement of records. So it's somewhat different because count of J tells us where to move R sub J instead of indicating which record should be moved into the place of R sub J. Did everyone get that distinction?
Say that again?
No.
So he's saying that even though it looks like an address table sort, which he describes earlier, like a couple of pages before, it's not exactly the same.
Mm-hmm.
Could someone explain how or what he means by that sentence?
I feel that the whole point is that with this new table, after sorting it, you can exchange the records in the original location to match the actual order that they should be.
So after this is done, how can you tell which one is the smallest unit? You can't really. If it was the first algorithm, then the smallest element is the one at index 2. Yeah, that's right. As opposed to, I lost my train of thought.
So my guess is that you would perhaps, naively, scan the list that you just sorted, and when you find, as you go, maybe every 2 elements, you find one you find the first element is the 2. So that means that the element, the item that is in that address, the equivalent address, both are sequential lists, right? So you can say the first element, the first object that you really want to sort actually goes to the third position in the list. So you will exchange it. And as you keep scanning the sorter indexes, you will exchange the actual objects to their proper place, presumably. And then you will end up with the sequential list of objects in the order in they're supposed to be, based on this one.
So if we had done an address table sort, how would that be different?
So I'm assuming that in the address table sort, you put the address where they're supposed to be, and you end up with a sequential list of addresses in the right order. So each address is pointing to the object. The object can be anywhere, doesn't matter, but the addresses are pointing to the right place. To the addresses. If you scan the list of the addresses, they will be in the proper order. Is that it? Ah. I didn't quite understood the address sorting. I'm kind of going with intuition.
Yeah, so address table sort is on
74. The second to last
74
paragraph.
and 75, right. So, yeah, the distinction seems to be that instead of working with the values, we're working with the positions of the values, the addresses of the values.
Right. So in this case, with what we just did, you might not need to move anything anywhere, as long as your code already takes into account that you don't have to scan the list over and over to know which is the first element. So you have to scan the whole sorted sequential list to find the 0, and that's your first element. That would be kind of weird. So perhaps you can do both. You can have the sequential list plus the address sorted somewhere, depending on the size of the object.
Well, you don't have to scan it. Well, if you want to know what goes in the first position, you have to scan it. Right. But if you just want to rebuild it, you just rebuild it in whatever order it is. So I think exactly. I gave the difference there in the comments. The first line tells you how to get with with an address table sort, and the second line is how you do the count sort.
Oh, I see. Makes sense.
Are you saying that with this counting sort, that's an easy way to find out the minimum?
Actually, no.
It doesn't look like you can find the minimum right away. You'd have to do the movement.
Well, after you've got that count, the very first item in the count is 2, and that's the minimum at index 2 minus the array of minus 2. I think the difference is, I liked what somebody said in the beginning, that this algorithm depends on your data to be sequential in memory. And if you were sorting something that was in a linked list or something that had variable length records, you would want to use an address table sort, because then you would sort the address table and sort by moving the address table around instead of counting.
Okay. Right.
I like that answer anyway.
Yeah. So count, so you're right. Like count of 0 will give you the index of the smallest value.
Right. So to find the smallest one, you'd have to scan the count list to find out where 0 is and use that index.
No, you wouldn't. I mean, that also works, but you wouldn't have to do that.
Yeah. That's
where I got stammered when I was first answering, and then I realized no, it's that first.
Then how would you find it?
Or is that true?
No. So the count is that. So the count 0 is saying the element that is in this index, the index 0, has 2 other elements below it. So you will need to have to scan the count list to find the one that has, the one with 0. The one with 0, so in the index in which 0 is the index of the element, the smallest element.
But in this
original
example,
list.
it also happens to be that the second element is the minimum, but I don't think that's, I guess that's not always true.
Right.
Yeah.
Yeah. Count of 0.
Count of 0 is 2, but that doesn't mean that the minimum element is at 2. It means that the element at 0 has 2 elements that are
So it's
smaller.
actually the offset or the position. It's telling you the position, the final position of that
Yes.
value at index
Which
0.
it does by counting the number of elements that are smaller.
Right.
Yeah, I got it. Okay. I think I got it.
Okay. So then, are we then saying that there's no easy way to find the smallest value without actually scanning the entire count?
Right.
That's what it seems. Yeah.
Mm.
It's funny that in this particular instance, the counts are also like they're also the if you go to that element, you find the the 2 means the count of 0 is 2 means that the array of 2 is the minimum, and count of 1 is 1 means that array of 1 is the minimum. That just happens to be. It wouldn't necessarily be the case for all inputs, I guess.
Yeah. Well,
Just
you're sorting for things, not getting too much randomness into it.
Right. That's kind of weird that happens to work.
Yeah, they're all matching up actually.
They do.
Yeah.
They do. But they can't. If you had a different order of input, would they always match up? I don't think so.
Okay. Well,
What exactly do you guys mean by that they match? So the index match, but what else matches?
so if you look at count of 1, so count of 0 is giving you the index of the smallest value in this case, and count of 1 is giving you the index of the second smallest value in this case, and count of 2 is giving you the index of the third smallest value in this case.
That's what I was saying, but I don't think that's true all the time when you run this algorithm. It's probably almost never true.
Okay, then maybe somebody can come up with a sample or an example while we move on. So let's go on to the actual algorithm. Actually, let's see here.
Yeah, 4312 will break it.
Okay.
Because the count of 0 will be 3, and
I was just curious if people like myself who use 0 relative indexing for the most part with, I guess, a lot of languages, get tripped up with the 1 relative indexing that's, I guess, used here, besides me.
Yeah, Knuth prefers indexing from 1. So yeah, that's something you have to kind of get used to.
Well, I've gotten down to the habit of saying, when I say index, it's 0 based. When I say position, it's 1 based.
Okay. All right. Yeah, well, index 0 is the first position. You can say it that way. All right. Let's. We still have a few minutes before 3, so let's look at the program quickly. The MMIX program. This is in the supplement, by the way. The MMIX supplement on page 74.
So this corresponds to the mix in Program C.
Yeah, so in volume 3 itself, it's still using the mix, the old computer, and then
Okay.
in the MMIX supplement, we've got the newer code.
Right.
Okay, so it's a little after 3. Let's take a break, and in about 10 minutes, we'll come back and we'll discuss the code and the remaining chapter and maybe work on some exercises. So feel free to turn off your cameras and mute yourself. Enjoy the break. See you. Okay. So, any questions about the code? Knowing the algorithm now, was there anything about the code that felt different in terms of the implementation, or anything about the MMIX portion that you wanted clarification on?
Yeah, I wanted to ask at least one question.
Uh-huh.
It's about jumps. So the jump is a relative address. It's a relative address. So I'm assuming that 0f means the next line, and 1f is skipping one line. Like, I don't really follow.
Yeah,
So
so
I
the
sort of follow the code, but I think I'm missing something by don't follow with the jumps.
okay. Did somebody want to explain it?
You're
About-
muted, Mike.
About the yeah, Michael, you're muted, by the way.
Oh
Yeah.
boy, I'm sorry. F means forward, B means backward, H means here. So when you see jump 1F, it means jump to the one here that is forward from this location, the first one. So jump this. There could be many 1H's, but when you say jump 1F, it goes down until it finds the first 1H, and that's where it jumps to. And if it says jump to B, then you go backwards until you find a 2H. To here. So it jumps forward or backward to a here.
So you're saying when it says jump 0f, it means jump to line 04 when they 0H?
Yes, exactly. Well, and there could be more than one. So it means the closest one that's after the current location.
Okay.
Which is weird.
Yeah, there is another 1H down below.
They used to do that back in the 70s.
Yeah, it's this idea of local symbols. Because with assembly, you don't have these scopes that you can define. So this is one way of limiting the scope of some symbol. It's by saying that it's the closest one that's either backward or forward, and then the definition or the location is the one that has the H suffix. Okay, anything else? So did the code match up with the algorithm? And by the way, I am going to step through this program in the demo afterwards, so we'll be able to see the actual values being used and the counts being updated. But yeah, if there's anything to discuss right now, we can do that. All right, so let's move on to the next algorithm. And we will read till about 326. Sorry, not 326, that's right. Okay, so can someone explain how this algorithm D works? And I've pasted the data from exercise 6 that Nuth mentions for working out this algorithm. So if you can just maybe show, again, just like before, how the count array would change.
Yeah, I'm okay. I'm a bit puzzled by this. Well,
Okay.
I understand the counting up to D3. And then you've got basically the size of the buckets you'll need for each thing when you do the sort. The accumulate, I'm not quite sure the value of that step.
Can someone explain what's
So
the point of D4?
So I'm not sure if I'm going to explain, but I'm going to try to see what I
Or
see.
whatever you understood. Yeah, that's great.
So first, so in the first pass, or in all the pass, so in D3, after D3, the count array is actually might be smaller than the list of Ks, right? Because if they are duplicates, then you will have for the 5, I think it will be like 2, then something like, right? If I'm getting it correctly. So count will be for the first 2 for 2 5s, 2 again for 2 zeros. No, actually not true. We'll go from the so we need to assume that we know what the range of the keys, which is from
Okay,
0.
so that's really the first thing. You have to know the minimum and the value. Sorry,
So,
minimum and the maximum.
exactly.
So what
you
is
go
that in this case?
from 0 to 9.
Okay, 0 through 9. So what does that mean about the array count?
So count will have 10 elements.
Okay.
Right. So we're going to start counting from 0. So 0. So the 0. So we're going to say so the 0 key has a 5. So we're going to choose. Wait. So we're going to go to the 0 key of. No, I'm missing something. Yeah, all the counts have 0 initially. So we have 10 zeros. Then D3, we're going to go from 0 to 9, increasing the value of that index, count of 0, count of 1, count of 2, count of 3. Every time we find something.
Okay.
Or we're going to go
so if we just look at the first,
around. We go through all the keys, and we say, okay, first key is 5. Let's go to count of 5, the count of index 5, and add 1 to it. Then we found a 0. Let's go to the count 0 and add a 1 to it. Then we found 5 again. Then we go to count 5 and add a 1 to it. 0. So we now will have 2 0 0 0. So after the first 4, it will be 2 0 0 0 2, and yeah, exactly. Right, exactly. So that's what we'll get after D3. So now we know how many of each is there? Is there? Yeah, it's kind of cool. And then in D4, we need to add everything that is below it. Yeah. So we're basically going to transform this in an array of counts by adding everything that is all the numbers that are below the index in your in. Like you start by if you're looking at index 2 by starting by 0, then you will have to then the third index will have 2 plus 4. Yeah, 2 plus 2. Sorry, is 4.
Okay.
Exactly. What James is writing in the chat.
Right.
Yeah.
And so what's the benefit of this?
So that's the counts, presumably. Yes. But as the counts, therefore we have the order. They just happen to be in the right order. Wow.
Okay, so from here you can say the first 2 is at position 5.
Isn't this giving us the same count as algorithm C now?
That's what I mean. That's my intuition.
So saying those,
But I don't understand why 7 is bigger than. Wait, no, not 7. I don't know, 9. Okay.
but so this all this tells us is that like I said, the first 2 is at position 5. Now, if all you need to know about it is that it's a 2, that should be okay. But he was talking about sorting things on their first digit, in which case there's like the number we're sorting on and this other data, which is also important. And this method would kind of lose that other data.
I didn't get that about the first digit. Why is the first digit significant?
Well, he said like you can sort large numbers by their first digit, so then you just get them partly sorted.
Oh, okay. By the leading, okay.
But then you still have the rest of the number you have to sort by later in the little subset, and we seem to be losing that in this sort. I mean, like think about a more more common use to be like sorting a long list of words. You do the first pass just on the first letter, and then you how many words beginning with A and how many words beginning with B.
How are we losing? How are we? I thought that this was the benefit of this algorithm.
Right, but I'm saying we're losing the other, like on the D4 account. We'll know that the numbers beginning with 2 start in position 5, but we don't know the rest of them, and they're like we haven't got them in that position yet, so we don't know what they are.
I don't see it. Like, so if I understand correctly, then you will go again and scan the original list. And you will say, okay, index 5. So 5 will go, you will go to the index 5 and you will find a 5 there. But then you will go to the 0 and the index 0 is a 2. Then you have 2 zeros?
Yeah, except this time the index actually refers to the value. The index of count is the value that that is in the original array.
0 goes in the second,
Yeah.
and 4 goes in the fourth. No, and 4 goes, wait, and 1 goes in the fourth place. Is it? Yes, it is. The fifth place. Is that it? No, that doesn't work.
No, so
I think I get it. I think I get it now. So after D3, after D3, it's a lot like algorithm C. Each number counts the number of occurrences of that. So like if D3 of 0 is the number of zeros, it's 2. D3 of 1 is the number of ones, it's 2. D3 of 2 is the number of 2s. And k equals 2 exactly one time, and that's what's in the count at D3. Now at D4, what you're doing is you're making it more like algorithm C, where the count is the number of items in K that are less than or equal to that position. So for 0, there's 2 zeros. For 1, you count both the zeros and the ones. There's 2 ones and there's 2 zeros. And then when you're ready to output, the output is going to happen in kind of a strange fashion. You're going to look at that first index of 2, and that's where you're going to put the 0 at index 2, but you subtract 1 first. So the first 0 goes at position 2 minus 1. So the first 0 goes actually at position 1, and you subtract 1 from that 2.
Isn't it?
And then the second 0 goes at. Is that right? I think that's right, but that's not stable, and I think he said later on that this was stable. But anyway, that's the way I understand it. So then when you get to the 4, that's saying that count of 1 is saying that the ones go. The last place for the 1 to go in the output is number 4. So you move and subtract 1, and you go all the way down the list.
Yeah. So let's say that we're indexing from 1 for the original array.
It makes more sense that way. It's easier.
Yeah, it makes more sense. It's a little easier because then you don't have to subtract anything, because then the first entry of count is telling you the last index where that value, in this case 0, will occur, right? So you started from 1, you go up to 2. You fill slots 1 and 2 with 0. And then you go into count of 1. So now we're looking at the value 1.
Places where you're going to put the 1. The first
yeah,
thing
the places where you're going to put
a 1 at position 4.
Until position 4. You keep putting a 1 until position 4, right?
That would make it stable. I was working backwards from 4 and then 3. Yeah, that would make it stable.
And then a 2, because we will stop at 4 with the ones, and now we continue with the value 2, and its last index is 5, which means there's just 1 slot for a 2. It fills that, and then we move to the next index of count, which is 3, which means the value 3. So how many 3s are we going to put?
None, because
none. Yeah, because we don't have anything beyond 5 to put a 3 in there. So 3 is not in the original array, which makes sense. And then we go to index 4 of count. The max position for that is 6. So after 5, we put a 4 there. We're already at position 6, so we stop with that. So yeah, does that sound right?
I mean, that makes sense.
Okay.
I still don't see don't identify it in the actual, step.
What do you mean you don't see it defined?
The feeling. So that would be the step 6, right? When we fill it up the stuff, right?
Yeah.
Yeah. I mean, it's okay. I get the idea.
I think maybe what you are not realizing, or to clarify it, S and R. So S is that destination area that's going to be filled.
Mm-hmm.
So when they're saying S sub I, that's the final region for moving the record. So they're going to copy the whole record that's associated with the key at J.
Yeah.
That's what it is.
I think this is putting things in backwards. Like when you look at D4, count of 0 is 2. So it says that the first 2 cells are going to be filled with zeros. If you look at it, it puts it in at 1 first, and then at 0. I think.
Okay, that's interesting.
Right. Yeah. Because it starts at the count that starts at the high number, and then kind of moves and then lowers the index count.
Lowers the index, but you're going from left to right, so.
Right.
So that's not the first thing that it does, actually. The first thing that it does is it looks at position 5, and position 5 has a 0, 1, 2, 3, 4, 5, 9. So it's that 9 represents that there are 9 elements up to and equal to 5. It puts the first 5 from K of 0 in at position 9 and subtracts 1 so that the next 5 would go at position 8 when it encounters it. Then it goes to the 0. That's the second iteration of the loop. Count of 0 is 2, so it will put the 0 in position 2 of the output array and subtract 1 from the 2. So now now D4 count of 0 is going to be 1, and the next 0 that it encounters will go to the first element of the array.
That sounds right.
Which I said when I was going through it the first time, that's not stable. It's backwards. So the zeros, the first 0, the leftmost 0 in the array went after the rightmost 0.
But it's counting down. Look in D5, it counts down.
It does count down. Yeah, it works.
No, from the source it counts down.
Oh, you go backwards. Okay, that'll make it stable. Yeah, okay, great. Yay!
Okay, good.
I missed that part. There you go.
James, going back to the point that you were making about being able to use the leading digits of keys. Let's say that you had like a huge range of values in the keys. It's not 0 through 9, but 0 through 1 million. Mm-hmm. Then how does this help?
Okay, so you're going to have the first digit is 0 to 9 if you go to 9999. So you then sort those. Now you have 100,000 numbers between 0 and 100,000, and 100,000 numbers between 100,000 and 200,000. So you have a much smaller segment to sort on your next pass.
It's even smaller than that. Who says you had 1 million numbers to start off with? You may be giving 1,000 numbers between 1 and 1 million to sort.
Okay,
So
let's say we have 1,000 numbers between 0 and 1 million. And so we sort on the first digit. What could happen that could be really beneficial?
You would have you would sort them on the first digit, which is which takes a lot less time, and then now you have 10 buckets of around 100 numbers each, because you started with 1,000 and you're putting them into 10 buckets. The ones that start with a 0, you have to pad them out with zeros. The ones that start with a 0, the ones that start with a 9. So you know the 100 or so that are at the end of the list, you know the 100 or so that are at the beginning of the list, and it's a lot easier to sort 100 than it is 1,000.
And not only that, but what else will happen with those 100 numbers when you've partitioned them?
I don't know.
Very good.
In my mind, there's another benefit, which is you will cut down on the range for those secondary sorts, right? So the 100, you may now have like 100 numbers, and the range of those numbers may be much smaller, than 0 through 1 million. In many of the buckets, you may have ranges that are, 0 to 1,000 or whatever that bucket corresponds to. Like that range would not necessarily encompass the entire rest of the digits. So yeah, so I think that sounds really great, actually. So in terms of like a first pass or second or even 2 passes, because it is, what is the complexity? How many passes are we making through the array?
At most 6. 1 for each digit. But the I'm counting like when you do the first digit, that's 1 pass. When you do the second digit, it's 10 chunks of the array, but you're going through the entire array again in 1 pass. I'm counting that as 1 pass.
Yeah, but I don't see a nested loop here. It appears to be.
In this algorithm, there isn't a nested loop. This is just what you do on one of the digits.
Right.
Yep.
This algorithm D that he's given here is just describing the algorithm that you would use to sort when you have a lot of duplicates. And if you're taking the example of 1 million sorting numbers between 1 and 1 million, and you have 1,000 of them, you would apply this algorithm up to 6 times until you were done. Might not be 6 times because but it could be as many as 6 times.
Right. Yeah. But it was just, let's say, just 1 pass of the 1,000 to get them in their buckets.
One pass of the 1,000 to get them in their buckets, and then the buckets are arranged from 1 to 99,999, and then the next one is from 100,000 to 100,000 to 199,999.
Right. Yeah.
And then you've got them sorted by their leading digit after you've applied this algorithm 1 time. Now you have 10 smaller buckets to sort, and you have to go through each of those 10 smaller buckets and sort and apply the algorithm again.
Okay. Yeah.
But, yeah. If
Nice.
the algorithm is n² running time, then it's really the first pass that's taking all of your time.
Mm-hmm.
And this algorithm actually isn't n² running time. It's
2n.
Yeah.
Yeah. Okay, very nice. Let's look at a few exercises, pages 79 through 80. And then there's a few in the MMIX supplement as well. But let's first just look at volume 3. So exercise 1 is asking if algorithm C would work if I goes from 2 up to n in step C2 instead of from n down to 2. Oh, okay. So if we did the comparisons from the left, starting from the left, when we're trying to figure out how many values are less than the current value, would it still work if we go from left to right? We have that example or a couple of examples above. The comparison is less than, right? So it's, if we look at Michael's example that he gave, which was 4, 3, 1, 2.
Yeah,
And
it'll work either way. Even if you're counting less than or equal, it would still work. Although for algorithm C, you got to count less than. It wouldn't matter. You could be counting greater than or less than. It doesn't matter which way you go. So the question is whether it works, whether you're going forward. The algorithm presents, I'm going to go backward. And I think the only reason you go backward is because it's easier to test when you're at the end of the loop. When you write in mix, in MMIX.
Okay, so what if j goes from 1 up to I minus 1 instead of I minus 1 down to 1?
Oh, j. Let's see, j. My guess is it still works. Sure, it would work. You're still comparing the exact same elements, just in a different order.
Yeah. Well, I assume it, as a general principle, it'll work. You might have an off by one error, which you have to tweak one way or another, but you can get it to work.
On C4, all you're doing is comparing all the KIs and KJs. Mm-hmm. And you're comparing them. The loops are set up so that I is greater than J, so that you're not comparing the same two keys. You're not comparing the same two keys, like you're never comparing KI to KI, and you're never comparing KI to KJ when I is greater than J. But that's all you need to do. Those are the only things that you need to compare. And no matter how you do the loop, whether you go across or whether you go down, whether you go from the top to the bottom or the bottom to the top, it's not going to matter. You're going to come up with the same answer.
Right. That's what I said. The principle is right. It'll work. But, you know.
But it's not even a matter of tweaking. It's already tweaked. If you were going to tell me C3 going from J equals I minus 1 to, or from 0 to I minus 2, yeah, that would not work. But on C3, you let J go from 1 to I minus 1, or from I minus 1 to 1, you're going to get the same answer.
Okay. Exercise 7 is asking what we were discussing earlier. Is algorithm D a stable sorting method? So
I
would
thought
it?
it was. I think I already answered that one. It's stable if you catch the fact that it's also outputting things by scanning the array backwards. If you scan it forward, it's going to be unstable.
Okay.
So yeah, we already answered that one.
All right. Yeah, it's important, and that's why he has those records associated with the key. So you're not just dealing with the values. Okay. Let's see. The rest of them are kind of like design your own algorithms to do certain kinds of sorting. And yeah, so, I forgot to ask this earlier, I should have, but I asked last weekend as well. Should we meet next Saturday after Thanksgiving, or will people show up?
I'll show up, but this is the pandemic. I got nowhere to go. No one's coming over here.
Yeah.
Actually, my daughter and son are coming over, but that's it. So we're not going to have a big Thanksgiving. I went to school at Michigan State University, so we had we have a tradition which will break this year of somebody hosting a big Thanksgiving party, which they called the bloat.
Okay.
And we would go to somebody's house, and it would be like, maybe, I don't know, there's probably around 50 of us. So, or maybe not quite that many, but
your audio got disconnected for a few seconds. But I'm assuming you're talking about some football game?
No, not at all.
Then what was the thing about Michigan State?
I graduated from Michigan State, and around 1980. That's another long story. It's somewhere between 1980 and 1992.
Yes.
But after we all got jobs, we moved to different states, and a lot of us ended up in New Jersey. Some of us ended up in Texas. Every year around at Thanksgiving, well, actually, look, a lot of us that were friends at Michigan State, we came from other states, and so in our college years, there was a large segment of our group that did not go home for Thanksgiving because it was just too much to travel. And it was only 2 days. So they had a Thanksgiving party at Michigan State, which they started calling the bloat.
Okay.
And
I think
we still have
got
that.
it.
We've had that for 30 years now. But we've had it out here every year. Somebody's had the bloat, and it's not going to happen this year because of the pandemic. It's the first year since I graduated in whenever it was that I graduated.
Has no one proposed some virtual substitute?
Oh yeah, there is a Zoom meeting.
Okay.
Yeah, there is a Zoom meeting. We actually have a brunch every month. And that turned into Zoom, so there'll be a Zoom, I guess.
Oh wow, you guys have really kept in touch. That's so great.
Yeah.
Okay, I will be. Fingers crossed.
Okay, cool. Yeah. I think from last weekend, Miguel and Arthur also said that they would be able to attend. So okay, I'll go ahead and schedule it.
I didn't finish.
Oh.
I will be closing on a house on Tuesday.
Oh my.
So next Saturday, I may be living in a place without internet connection yet. So.
Okay, well, you can always use your phone.
I will try. I'll see what I can do.
Yeah. All right, great. So I'm going to start the walkthrough in the debugger of Program C. And let me just set that up. Okay, how is this font size? Is it good?
Works for me.
James, is that good for you?
Yeah, it's good.
Okay. All right, so we've got algorithm C, which is the sort function or subroutine down here. And up here, we're setting some of the registers. So K is going to be the address of the array that we're going to sort. And then count has the address of the count array that we're going to fill. And then N is the register that will have the number of elements. And then there's some registers for local variables. So the data that we're going to sort is down here. That's the data. That's the example that I'd given earlier. And it's got 4 values in there. And then right after that array, we've got the count array. And it's just initialized, like the first octa is initialized. All of these values are going to be octabytes, 8 bytes. And so that first value is initialized to 0. But then what we're doing is with this lock directive or the location directive, we're reserving the space needed for counts for each one of those values. So that's why you have this little formula over here that takes into account the size of the data array. And then following that, there are 2 hard-coded arrays for the expected results. So there's 2 results that we'd be interested in. What is the correct count array and what is the correct sorted array? So this is just for inspection. We're not actually going to do the verification. And then there's a little main program down here that will call the sort function. The sort function takes 3 parameters. There's the address of the array, there's the address of the count array, and then the third parameter is the size or the number of elements of the data array. The main program doesn't save any registers, so it's just doing a push J0, meaning no registers will be saved, and just called sort. So I'm going to start the program. We won't be needing some of these windows, so I'm just going to close them. There we go. All right, so main starts off and register 1 now has the address of the data array, register 2 now has the address of the count array, and register 3 has the number of elements. So we can see there are 4 elements. You can see the addresses, right? So here's the address of the data array, here's the address of the count array, and down here in these memory panels, I've just entered those addresses. So this first memory panel is showing the data array, and these first 4 values correspond to, 5 and what's the second one? Is it, let's see, 5 minus 2 minus 3 minus 6. Okay, so this is 5, obviously, then this is minus 2 minus 3, and then 6. And then the bottom memory panel is showing the count array. So 1, 2, 3, 4. These are what's going to be used for the count. So now we get into sort. We initialize a loop to set each of the count values to 0. So initializing the count array. They just happen to be 0 to begin with, but we're just initializing them. So this will just go through this loop 4 times. You'll notice line 36 has the store constant instruction, which is a convenient way of setting some small value in memory. And I is a counter, but because we're using it as an offset into some base address for an array, that offset needs to be in octabytes. So that's why it's being scaled by 8 whenever we change it. And this is a shift left, and it's shifting left by a power of 2, which is 3 in this case, which is multiplication by 8. So that's why that is there. And so we'll go through this 4 times, and it will just set everything to 0. We won't see anything change over here because all the values in memory are already 0. And then the last time, okay, so now we go into the main sorting loop, and we've got the nested loop. So there's an outer loop on I, and there's an inner loop on J. So the first pass of the loop, we are initializing I to be the value of n, and again scaled to octabytes. So we're shifting it left 3 bits, multiplying by 8, and then we jump into the body of the loop so that the first iteration gets kicked off. And here we're decrementing I. We're setting J to the equivalent of I minus 1. Okay, and remember this is, we're going backward, just like in the original algorithm. So J will start off at I minus 1. So it takes whatever there's in I and subtracts 8 from it, again because of the fact that these are actually being used as offsets. And we go to the start of the loop, the outer loop. So we load the current value of the count for the last value right now, which is 6. So that'll be 0. And then we get the actual values. So register 5, which is being called KI, that should show a 6 at this point. Yeah, so that's what we see here. And then we get the value that we want to compare it with, which is at the slot before the last one. And so that value is a minus 3, I guess. Let's look at it in decimal. Yeah, it's minus 3. In fact, we can just keep these as decimal for now. So we do the comparison. 6 compared with minus 3, and we use the CMP comp instruction. It will put the result of the comparison into this register, which is register 9. Let me show that one here because it'll appear. and it'll be positive. I think it's a +1 if the first value or the first operand is greater than the second one. It's 0 if they're equal, and it's -1 if the second operand actually, because the first operand is the destination register. So the second operand compared to the third operand. Okay, so we do the comparison, we get a +1 as the result, which means that k of I is greater than k of j. And in that case, we are going to do a branch to set the count for I, because its entry turned out to be the greater one. So that count of I gets incremented, and we go on to the next j. We decrement j so that it moves to the next value. And then we check if we need to branch. And in this case, we go on. So if you'll notice, we didn't write the value of the new count to memory yet. So we won't do that until we're done with I. So we go through this loop again. We do the comparison with -2, and 6 is greater than -2. So the count now goes up for 6. Notice that the count it's going up by 8 increments of multiples of 8, because it's going to be used as an offset into the count array. So this is actually, saying that there's 2 values that we found that are less than the current k of I so far. But this is going to tell you like what's going to be the eventual offset that you would need to move k of I to. So that's why it's showing up as 16, because it's going to be in terms of octabytes. And so we keep going. 6 is the biggest value, so we should end up with 3 in there before we're done. And now we're done. The j counter reached the beginning of the array. So now we write the value of the new value of count for k of I back to memory. And down here, you can see that for the 4th slot, we've set it to, let me make this decimal as well. Oops. Signed. Yeah, I guess it doesn't matter. It could be unsigned here either, as well. So that's in terms of octabytes again. So divided by 8 means there's 3 values that were less than the value that's in index 4 of the original array. And at this point, because we've gone through one full pass of the inner loop, we have to now reinitialize the j counter to I minus 1 again, right? I's gone down from n to n minus 1, so now j will get reinitialized to n minus 2. And the value that we're comparing, let me make this signed as well. So the value that we're comparing now is -3. and it'll be compared to -2 and then 5. So that, go through the loop again, do the comparison of -3 and -2, and -3 is smaller this time, so it'll be the count for -2 that is going to get incremented. So let's see that happen. In this case, we're going to fall through because the result is -1, and this is a probable branch non-negative, so we're not going to branch. So we go to this line 70 where the count for the j, or the value corresponding to the j index, is going to be incremented. And so first of all, we have to get that current value from memory. So we do this load octa into register 7, which is being called CJ. And so that will be 0 right now. So that's why nothing got highlighted over here. But now we're going to add something to that, add 1, and scale it to octabytes. So you see an 8 appear here. For J, we need to write this to memory right away because we'll be moving on, right? So that's why there is a store instruction right after the increment. So that's going to be written to the count for the thing that was at index 2. And continue the loop. Right, so notice over here, this is the first time we did this. We had incremented the count for j, so we want to make sure that we're skipping over the increment for loop I. We're still in the nested loop, and so that's why there's a jump here, jump 5f. As Michael explained earlier, this is referring to 5h down here in a forward direction. So we decrement j and then keep going for the next pass through the loop. And same thing happens here. This time, -3 will be compared with 5. And it will turn out to be less than -3 compared with 5. So did I say that right? -3. Yeah, -3 got compared with 5. It turned out to be less than, so now we have to increment the count for 5, right? Yeah, so that's what's happening here, because 5 corresponds to the j, the loop over j. So just like before, what we did with -2. So we were going to increment and store the count for corresponding to 5. And so that gets an 8. And then we're done with the inner loop again. So we now have to decremented J and now we have to start the next iteration of the outer loop. So we should be now looking at -2. So we load the count for -2. So far, we load the value itself. So in $5, we get that -2. We do the comparison with the value that's just before it, which will be a 5. So we load that. And we didn't get it. We didn't see any highlighting because that 5 just happened to be in that register from before. And then we do the comparison. And -2 is less than 5. So in T, which is this result register, you get a -1. And again, because it had a -1 from before, there's no highlighting. But because -2 turned out to be less than 5, we have to increment the count for 5, which is corresponding to the J loop. So that's what's happening here. We increment that count and we write it to memory with the store. And so that first value turns into a 16. And then we count down the J loop. In this case, when we decrement J, we should find out that we're at the end of the inner loop. So that branch was not taken. Okay, so that's the end of that inner loop, which means we now need to write the updated count for K of I after it's done with all the comparisons. So write that. In this case, it didn't get updated because there was no value that was less than -2 that was found. So we're done with the inner loop. So now we have to decrement the loop for the outer, the counter for the outer loop, which is I. So we decrement that. We reset J to I -1. And in this case, we would have reached the end of the outer loop as well, because we're now at that last or the first value, and there won't be anything to compare before that. So that's the end of the outer loop, and the entire count array should be now correct in terms of the values that are less than or equal to, a particular original a value in the original array. So we now have the count array down here. Okay, so there's this final pop, which is just a return. There's no return value here because we just updated the count array in memory, and that's basically our result. So there's nothing to return. That's why it's a pop 0. And this second 0 is, if you remember, it just tells you what is the offset to return to compared to where you jumped from. So This is saying just return to wherever you jumped from. You know, nothing to offset over there. So when we return, we're going to return to the jump instruction, which was down here. So we'll return to just after this, which will be over here. So let me do that. And that's what happened. And $255, this is the permanent global register, and it's used for the return value of the program, the exit status of the program. So that's just being set to 0 for success. And then, you know, the trap and the halt is just to stop the program. So let's just make sure that the count array is correct. We can do that by looking at the expected data that I had hard coded over here. Yeah, so here we go. So this is the expected count, and it should correspond to this sorted array, which we can figure out using the count values. But so what is this saying? It's saying 8 times 2, which is 16 in the first slot. Yeah, we see that. 8 times 1, that's 8 down here. So that's good. 8 times 0, which is just 0. So that's good. And then 8 times 3, which is 24. So that is correct. So that was the walkthrough for this. Anything I can explain a bit more, James? Anything about MMIX or the walkthrough? Oh, Michael's also still here. I thought maybe you had stepped away.
Yeah, I think
Okay. Michael, you were frozen there for a few seconds again.
Yeah, I was here. My camera just glitched.
Okay. All right. So everything look good?
Looks good to me.
All right, cool. So we shall meet next Saturday, and we will continue with whatever is next in the sorting sections.
Okay, great.
See you then. Thanks a lot.
Thank you, Sataj.
Yeah. Bye-bye.
I said thank you.
Yeah, I got it.
okay, bye-bye.
All right. I never know how to close this except by Xing out. I guess that's the way you do it.